Welcome! Today, we'll dive into an exciting problem from LeetCode, number 1755, closest subsequence sum. We'll explore different approaches, analyze their complexities, and discuss the best strategies to solve this problem. Let's get started. In this problem, we are tasked with finding a subsequence of an array nums whose sum is as close as possible to a given target value, called goal. To quantify this, we minimize the absolute difference between the sum of the chosen subsequence and the goal. A subsequence is simply a sequence derived from the original array by removing 0 or more elements, without rearranging the order of the remaining elements. For example, if the array is 5, 7, 3, 5, 5, 3, or 5, 7, 5 are valid subsequences, but 3, 5, 7 is not because the order is changed. The task is to return the smallest possible absolute difference between the sum of any such subsequence and the goal. The constraints specify that the array can have up to 40 elements, with each value ranging from -10⁻7 to 10⁻7, and the goal can be as large as 10⁻9 in absolute value. Let's look at the first example to understand this problem better. Here, the input array is nums equals 5, 7, 3, 5, and the goal is 6. One possible subsequence is 5, 5, which sums to 10. The absolute difference between 10 and 6 is 4. Another option is -7, 3, 5, which sums to 1, giving an absolute difference of 5. However, the subsequence 5, 7, 3, 5 matches the goal exactly, as its sum is 6. Since the absolute difference is 0, which is the smallest possible, the output for this example is 0. This illustrates how the problem asks us to find the subsequence that minimizes the absolute difference between its sum and the goal. Now consider the second example, where nums equals 7, -9, 15, -2, and the goal is -5. For the subsequence, -9, -2, the sum is -11, and the absolute difference from the goal is a -11, -5, equals 6. Another subsequence, 7, -9, -2, sums to -4, with an absolute difference of a -4, -5, equals 1. In this case, the smallest absolute difference we can achieve is 1, so the output is 1. This example highlights how different subsequences can be compared to identify the one that brings us closest to the goal. Finally, in the third example, we have nums equals 1, 2, 3, and goal equals -7. Here, the closest possible sum is 0, which can be achieved by taking an empty subsequence. The absolute difference between -7 and 0 is -7, 0 equals 7. Therefore, the output in this case is 7. The constraints remind us that while generating all possible subsequences is computationally expensive due to the exponential growth of subsets, the problem can be solved efficiently using techniques like the meet-in-the-middle approach or binary search on subset sums. These methods allow us to handle the large range of values and constraints effectively. To solve this problem, we first considered a brute force approach. The intuition behind this method is straightforward: generate all possible subsequences of the input array nums, calculate their sums, and then determine which sum has the smallest absolute difference from the target value, goal. This can be implemented using recursion or bit masking to systematically generate all possible subsequences. Once we have all subsequence sums stored in a list, we simply iterate through the list to find the minimum absolute difference from goal. While this approach is conceptually simple, it has significant limitations. The time complexity is 2 to the power of n, as there are 2 to the power of n subsequences for an array of size n. Similarly, its space complexity is also 2 to the power of n, because we need to store all of these sums. This makes the brute force approach impractical for larger arrays, especially when n exceeds 20, as the number of subsequences grows exponentially. Thus, we need a more efficient strategy for tackling larger inputs. A more optimized approach is the meet-in-the-middle strategy. The main idea here is to avoid generating all subsequences at once by splitting the problem into two smaller parts. We divide the array nums into two halves, referred to as left and right. Then, we compute all possible subsequence sums for each half separately using brute force, which is manageable because the subsets are smaller. Once we have these sums, we sort the sums of one half, such as right, and for each sum in the other half, we use binary search to efficiently find the closest match to goal. This method takes advantage of the fact that binary search significantly reduces the time required to find the closest pair of sums that minimizes the absolute difference with goal. Key observations here include the ability to pre-compute subsequence sums for smaller subsets and the reduction in complexity by working with two halves. The effective time complexity is reduced to O(2)n/2 log 2(n/2), and the space complexity is O(2)n/2, as we only need to store sums for one half. This trade-off between pre-processing and efficient searching makes the meet-in-the-middle approach highly suitable for larger inputs. Additionally, while alternative heuristic methods, such as greedy approaches, can be faster, they are unsuitable for this problem because they do not guarantee an optimal solution. The meet-in-the-middle approach was chosen because it offers the best balance between efficiency and correctness. The brute force approach, while simple, becomes computationally infeasible for larger inputs, as the exponential growth in subsequences makes it impractical. On the other hand, meet-in-the-middle significantly reduces the problem size by splitting the array into two smaller halves and leveraging binary search to efficiently find the closest pairs of sums. This ensures that we explore all possible sums, unlike greedy methods, which might miss the optimal solution. Furthermore, meet-in-the-middle is scalable, handling input sizes up to n equals 40, which aligns with the problem's constraints. However, this strategy does have its trade-offs. The increased efficiency comes at the cost of additional memory usage, as we need to store the sums of one half. For very large inputs, this memory requirement could become a limiting factor. Additionally, the implementation is more complex compared to brute force, as it involves dividing the array, managing subsets, and performing binary search. Despite these trade-offs, the meet-in-the-middle approach stands out as the most effective solution, striking a balance between computational efficiency and correctness while adhering to the problem's constraints. To understand this problem, we're tasked with finding the smallest absolute difference between a target value, called goal, and the sum of any subsequence of the given array nums. A subsequence is essentially formed by taking 0 or more elements from the array in their original order, but without needing to use all the elements. For example, if the array is 1, 2, its subsequences include 1, 2, and 1, 2. The brute force approach to solving this problem involves three main steps. First, we generate all possible subsequences of the array. This can be done using recursion or bit masking, where each element is either included or excluded, resulting in 2(n) subsequences for an array of size n. Next, we calculate the sum of each subsequence and store these sums. Finally, we iterate through the list of sums, calculate the absolute difference between each sum and the goal, and track the smallest difference encountered. While this approach is straightforward, it requires us to handle an exponential number of subsequences, which can be computationally expensive for large arrays. To implement this brute force approach, we need efficient data structures. The first step, generating all subsequences, can be achieved using either recursion or bit masking. In the recursive method, we construct subsequences by deciding for each element whether to include it or exclude it. With bit masking, we use binary representations to indicate inclusion or exclusion, where a 1 means the element is included, and a 0 means it is excluded. Both methods allow us to systematically generate all possible subsequences. Instead of explicitly storing these subsequences, we can optimize by directly calculating and storing their sums during the generation process. These sums can be stored in an array, which enables efficient traversal when we later search for the sum that minimizes the absolute difference with the goal. This setup ensures that we're focusing on the sums of subsequences rather than the subsequences themselves, which can save both time and memory. It's important to recognize some key insights about this brute force approach. First, the sheer number of subsequences grows exponentially with the size of the array. Specifically, there are 2(n) combinations. This makes the method computationally expensive and limits its feasibility to smaller arrays, typically when n is 20 or less. To optimize, we can avoid explicitly storing all subsequences and instead compute sums on the fly. This reduces memory usage significantly. Another optimization involves pruning, where we terminate the recursion early if we know the current sum has already diverged too far from the goal. Additionally, we need to account for edge cases. For example, if the array is empty, the only valid subsequence is the empty subsequence, which has a sum of 0. For arrays with negative numbers, we must ensure that sums are calculated correctly. Finally, for larger arrays, brute force simply becomes impractical, and more advanced techniques such as the meet-in-the-middle algorithm are necessary to handle the exponential growth. When analyzing the complexity of this brute force approach, the time complexity is dominated by the generation of all subsequences, which requires O(2 to the power of n) operations. Calculating the sums of these subsequences and finding the minimum absolute difference each add another O(2 to the power of n, resulting in an overall time complexity of O(2 to the power of n. Similarly, the space complexity is also O(2 to the power of n, since we need to store the sums of all subsequences. These exponential complexities highlight the main limitations of the brute force method. It struggles to scale for larger input sizes, both in terms of computation time and memory usage. Despite these drawbacks, the brute force approach is valuable as a baseline for verification, ensuring correctness before implementing more sophisticated solutions. Techniques like meet-in-the-middle or binary search over sorted subsets of sums can significantly improve efficiency while maintaining accuracy. These advanced methods are essential for handling larger arrays where brute force becomes impractical. Here, we begin by importing the combinations function from the itertools module, which will help us generate subsets of the input list. The solution is implemented within the min-abs difference method of the solution class. The first step is to split the input list nums into two halves, left and right. This is because dividing the problem into smaller parts allows us to handle subsets more efficiently, especially when the array size is large. Next, we define the helper function generate_subset_sums that takes an array as input and generates all possible subset sums. This is done by iterating through all possible subset sizes, from 0 to the length of the array, and calculating the sum for each combination of elements. The results are stored in a set to avoid duplicates, and we return these sums as a sorted list for easier processing in the next steps. Using this helper function, we compute left_sums and right_sums, which represent all possible subset sums for the left and right halves of the array, respectively. Finally, we initialize two pointers, L and R, to traverse these sorted lists, and a variable closest to track the smallest absolute difference between the goal and any subset sum combination. Now, we apply the two-pointer technique to find the closest sum to the goal. The idea is to start with the smallest value from left_sums and the largest value from right_sums and calculate their sum. If this current underscore sum is less than the goal, we move the left pointer L forward to increase the sum. Otherwise, if the current underscore sum is greater than or equal to the goal, we move the right pointer R backward to decrease the sum. At each step, we update the closest variable to hold the smallest absolute difference encountered so far. This approach ensures that we efficiently search through all possible combinations of subset sums without redundantly iterating through all pairs. Once the pointers have fully traversed their respective lists, we return the closest value, which represents the minimum absolute difference between the goal and the sum of any subset combination. Here, we begin by importing the necessary libraries and defining our solution class. The main method, min-abs difference, receives an array of integers, nums, and a target value, goal. The first step is to split the input array into two halves, left and right. This is done using the arrays.copyOfRange method, which ensures that we can process smaller portions of the array independently. Next, we generate all possible subset sums for each of these halves by calling the generateSubsetSums method, which we will discuss later. These subset sums are stored in lists called left sums and right sums. To optimize the process of finding the closest sum, we then sort both lists in ascending order using collections.sort. After this, we initialize the variable closest to store the minimum absolute difference encountered so far, starting with integer.max_value. Finally, we set up a two-pointer approach, with one pointer starting from the smallest value in left sums and the other starting from the largest value in right sums. By iterating through these lists, we calculate the current sum of the two pointers, update the closest difference if needed, and adjust the pointers based on whether the current sum is less than or greater than the goal. Now, if the current sum is less than the goal, the left pointer increments to explore a larger sum. Otherwise, the right pointer decrements to explore a smaller sum. This process continues until the pointers either cross or we exhaust one of the lists. Once the loop completes, the closest variable holds the smallest absolute difference between any subset sum and the goal, which is then returned as the result. The generate subset sums method, used earlier, is also defined here. It takes an array as input and generates all possible subset sums. The method uses a bit masking approach, where each subset corresponds to a binary representation of numbers from 0 to 2 to the power of n1, where n is the length of the input array. For each subset, we iterate over the bits of the binary representation, checking if a specific element in the array should be included in the subset sum. If the bit is set, the corresponding array element contributes to the sum. These sums are collected in a list, which is then returned. This method ensures all possible subset sums are computed efficiently, forming the foundation for our two-pointer search. In this problem, we aim to find the smallest absolute difference between a given target, called goal, and the sum of any subsequence from an input array, nums. To solve this efficiently, we use a technique known as the meet-in-the-middle strategy. Let's start with an example where nums equals 5, minus 7, 3, 5, and the goal is 6. The first step is to split the array into two halves. Here, the left half contains 5, minus 7, and the right half contains 3, 5. This division will allow us to independently calculate and analyze subsets of each half before combining their sums to find the closest match to the goal. The next step is to generate all possible subset sums for each half of the array. For the left half, we calculate the sums of all subsets. The empty subset gives 0, the subset 5 gives 5, -7 gives -7, and 5 minus 7 gives -2. Sorting these results, we get left underscore sums as -7, -2, 0, 5. Similarly, for the right half, the subsets are, with a sum of 0, 3, with a sum of 3, 5, with a sum of 5, and 3, 5, with a sum of 8. Sorting these, we get right underscore sums as 0, 3, 5, 8. Now, to find the closest sum to the goal, we use the two-pointer technique. We initialize one pointer at the beginning of left underscore sums, another at the end of right underscore sums, and start with an initial closest difference set to infinity. In the first iteration, we calculate the current sum as -7 from left underscore sums and 8 from right underscore sums, which totals 1. The difference between the goal and this sum is 5, so we update the closest difference to 5. Since the current sum is less than the goal, we move the left pointer forward. In the third iteration, the current sum is -2 from left underscore sums and 5 from right underscore sums, resulting in a total of 3. The difference from the goal remains 0, so the closest difference does not change. Since the current sum is still less than the goal, we increment the left pointer. Finally, when the current sum is 0 plus 5, the total becomes 5, and while the difference from the goal remains 0, there's no need to update the closest value. At this point, we find that the closest difference for this example is 0, meaning we managed to match the target exactly with a subsequence sum. Now let's consider another example where nums equals 1, 2, 3, and the goal is -1. Again, we split the array into two halves, the left half contains 1, and the right half contains 2, 3. Next, we calculate all subset sums. For the left half, the sums are 0 for the empty subset and 1 for the subset, 1, giving left underscore sums as 0, 1. For the right half, the subsets yield sums of 0, 2, 3, and 5, resulting in right underscore sums as 0, 2, 3, 5. Using the two-pointer technique, we initialize pointers and begin comparing sums. In the first iteration, the current sum is 0 from left underscore sums plus 5 from right underscore sums, totaling 5. The difference from the goal is 6, so we update the closest difference to 6. Since the current sum is greater than the goal, we move the right pointer backward. Continuing with the two-pointer approach, the next iteration gives a current sum of 0 plus 3, which totals 3. The difference from the goal is now 4, so we update the closest difference to 4. Again, the current sum is greater than the goal, so we decrement the right pointer. On the following iteration, the sum becomes 0 plus 2, resulting in 2. The difference reduces to 3, so we update the closest difference again. Finally, when the current sum is 0 plus 0, the total is 0, and the difference from the goal is just 1. This is the smallest difference we can achieve in this example, so the result is 1. For the last example, we have nums equal to 7, 4, -1, 2, and the goal set to 3. Splitting the array, the left half contains 7, 4, and the right half contains -1, 2. Generating all subset sums, the left half yields sums of 0, 4, 7, and 11, resulting in left underscore sums as 0, 4, 7, 11. For the right half, the sums are 0, -1, 2, and 1, which when sorted become right underscore sums as -1, 0, 1, 2. Using the two-pointer technique, we initialize pointers and begin the iterations. In the first iteration, the current sum is 0 from left underscore sums and 2 from right underscore sums, totaling 2. The difference from the goal is 1, so we update the closest difference to 1. Since the current sum is less than the goal, we move the left pointer forward. In subsequent iterations, we continue comparing sums, but no smaller difference is found, leaving the closest difference for this example as 1. To summarize, the closest differences we found across all three examples were 0, 1, and 1, respectively. By dividing the array, calculating subset sums, and using the two-pointer technique, we efficiently determined the closest subsequence sums to the target goal in each case. This approach ensures we achieve the optimal solution with reduced computational complexity. To analyze the time complexity of this solution, we begin by looking at the process of splitting the array into two halves, which takes constant time, 1, since it's just slicing the array into two equal parts. Next, we generate all possible subset sums for each half. For a half of size n/2, the total number of subsets is 2 n/2, and while computing each subset sum involves iterating through the elements, the dominant factor here is the number of combinations generated. Once these subset sums are computed, they are sorted, and the sorting step takes 2 n/2 asterisk log 2 n/2, which simplifies to 2 n/2 asterisk n/2. Since we repeat this process for both halves, the total time for generating and sorting subset sums becomes n asterisk 2 n/2. This subset generation step dominates the overall time complexity of the solution, as we'll see further on. The next key step is the two-pointer search, which is used to find the closest sum by comparing the sorted subset sums of the two halves. Each of the sorted lists, left underscore sums and right underscore sums, contains 2 n/2 elements. The two-pointer technique iterates through these arrays in linear time, which means this step runs in 2 n/2. When we combine this with the earlier step of generating and sorting subset sums, the overall time complexity is dominated by the subset generation step, resulting in a total complexity of n asterisk 2 n/2. For the space complexity, the storage of all subset sums contributes the most. Each half generates 2 n/2 subset sums, so the total space required is 2 n/2. Additionally, the sorting operation uses temporary space proportional to the size of the arrays, but this does not change the dominant complexity. Therefore, the space complexity is also 2 n/2. When we summarize the overall space complexity, it is clear that the storage for the subset sums is the dominant factor, leading to a total space usage of 2 n/2. To understand the efficiency of this optimized approach, we compare it to the naive solution. The brute force method would generate all possible subsets of the array, which is 2 to the power of n subsets for an array of size n. Iterating through all of these subsets takes 2 to the power of n time, and storing them requires 2 to the power of n space. In contrast, our optimized approach reduces the problem size by splitting the array into two halves. This reduces the time complexity to n asterisk 2 n/2, and the space complexity to 2 n/2, which is a significant improvement. This efficiency makes the optimized solution much more practical, especially for larger inputs. The time and space complexities remain consistent across all cases: best, worst, and average. Even in the best case, where the first computed sum matches the goal, the solution still needs to generate all subset sums and perform the two-pointer search, resulting in a time complexity of n asterisk 2 n/2, and a space complexity of 2 n/2. Similarly, in the worst case, where all possible sums must be inspected, the complexities remain the same. On average, the workload does not change since all subset sums are always generated and processed. The mathematical justification for this efficiency lies in the divide-and-conquer strategy. By splitting the array into two halves, the problem size is reduced from 2 to the power of n subsets to 2 n/2 plus 2 n/2 subsets. Sorting and searching through these smaller subsets is computationally feasible, thanks to the reduction in size. This approach is what allows the solution to handle inputs as large as n equals 40, making it both efficient and scalable compared to the naive method. When working on this problem, there are several common mistakes that can trip you up. First, it's easy to overlook edge cases. For instance, what happens if the input array is empty or contains only one element? Failing to account for these scenarios can lead to runtime errors or incorrect results. To avoid this, always ensure your solution is robust enough to handle edge cases, whether the input is empty, has a single element, or involves very large inputs. Another frequent error is relying on brute force to generate all possible subsequences. While this approach might work for small arrays, it becomes computationally expensive and leads to time limit errors for larger inputs. Instead, use optimized techniques like divide and conquer or pruning to narrow down the search space. Additionally, a common pitfall is calculating the absolute difference incorrectly. Some solutions forget to use the absolute value function, leading to incorrect results. Always compute it as abs, sum goal, to ensure accuracy. Finally, be mindful of memory usage. Storing all subsequences in memory can cause overflow for large inputs. To prevent this, opt for iterative or streaming methods to compute values without holding unnecessary intermediate data. Another common mistake is ignoring the problem constraints. For example, failing to consider the range of the input or the goal can lead to invalid assumptions, ultimately affecting your solution. Reading the constraints carefully is essential to designing an approach that respects the problem's requirements. Now, regarding interviews, this problem is a variation of the classic subset sum problem, which is often tackled using techniques like backtracking, meet in the middle, or dynamic programming. Recognizing this connection early helps you choose an appropriate approach. For large inputs, divide and conquer methods, such as splitting the array into two halves, can significantly reduce the exponential search space. However, it's important to weigh the trade-offs of each method. For instance, while dynamic programming offers polynomial time complexity for similar problems, it may not always be feasible here due to constraints on the goal. In some cases, greedy or heuristic methods might be more practical. During interviews, it's critical to articulate your thought process. Explain why you chose a particular approach, the trade-offs involved, and how you address edge cases. This structured communication is often as important as arriving at the correct solution. This problem also has strong connections to other problems on LeetCode. For example, LeetCode 416, partition equals subset sum, involves finding subsets with equal sums, which is a similar challenge. LeetCode 494, target sum, introduces the additional complexity of using signs to achieve a target value. Of course, LeetCode 1755, closest subsequence sum, is the problem we're focusing on, and it's often solved with the meet in the middle approach. Additionally, LeetCode 322, coin change, is another dynamic programming problem with overlapping optimization concepts. Now, let's consider some alternative approaches. One highly effective method is meet in the middle. Here, you split the array into two halves, calculate all possible subsequence sums for each half, and then use binary search to find the pair of sums that comes closest to the goal. This method is incredibly efficient for large inputs, but it does require additional space to store sums from both halves. Another option is backtracking with pruning, where you use recursion to explore subsequences but eliminate branches that exceed the goal or can't contribute to the optimal solution. While this approach is slower than meet in the middle, it's often easier to implement. Dynamic programming is another viable approach, particularly for smaller constraints. By maintaining a DP table to track achievable sums up to the goal, you can efficiently solve many variants of the problem. However, this method is limited by memory constraints, especially when dealing with very large inputs, as the DP table can grow significantly. In scenarios with extremely large constraints or when an exact solution isn't feasible, greedy approximation techniques might be worth considering. These heuristic-based methods aim to get close to the solution quickly, sacrificing some accuracy for speed. While these approaches won't always guarantee optimal results, they're practical under tight time constraints or when dealing with immense input sizes. Ultimately, the choice of approach will depend on the problem constraints, input size, and performance requirements, so it's crucial to stay flexible and adjust your strategy as needed. Great job! We covered the closest subsequence sum problem, reviewed key concepts, and discussed takeaways to help you in similar challenges. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!